Now, today's speaker is Jonathan Finley. He is a professor at TU Munich in Garching, which is not in Munich, but very close by.
We like to call it.
He is in an institute called the Walter Schottky Institute. He is one of the few professors I know in Germany who is not German. He is from the UK and did his PhD at University of Sheffield with Morris Skolnick, who I know quite well, and was a Royal Society Fellow. Is that correct?
That's right.
Okay. And Jonathan will talk about one of my favorite topics, semiconductor-based quantum optics.
So, Glenn, thanks very much for the introduction. And I'm also amazed to see so many people at the lunchtime seminar, and I figured out how you guys do it. You have the free lunch next door. But what was very pleasing is the number of people in here more or less correlates with what I saw next door, so it means there are not so many that come just for the free lunch. So it's very nice and very encouraging. So as Glenn mentioned, I've spent the last 10 years or so in Munich studying essentially how you can use light to control quantum states in horrible, dirty semiconductor nanostructures. Maybe if I get my presentation back. Well, that's good.
Not a nice butterfly.
We're going to have to go to a certain pace, otherwise it's going to switch off, yeah? And essentially what you're going to see over the next 45 minutes or so is that this involves kind of two different length scales you have to engineer. On the one hand, as you see in this picture behind, you have to engineer the way you deliver light to a particular nanostructure. So that is doing things like creating photonic crystals, which allow you to create cavities, allow you to engineer the way light propagates in a semiconductor material. And into this type of modified photonic environment, what we're doing typically is we're embedding zero-dimensional nanostructures, so typically quantum dots and single quantum dots, and these are optically active quantum dot systems. Now, why are we doing this? Why are we exploring this type of different semiconductor nanostructure? Well, many of you working in the field will know that in zero-dimensional nanostructures, many of the quantum degrees of freedom that you can interact with, things like, for example, the spin of an electron or the spin of an exciton in the system, actually are very robust quantities compared to higher dimensional systems like quantum wells. So this, if you like, is an archetypal quantum memory. Embedding it in some kind of photonic system allows you to interact with it. And the vision for the work we're doing, and I'll try to illustrate this in my talk today, is really to move towards a kind of scenario where you can create kind of essentially have qubits on a chip. You can have them exchanging photons, which are guided via photonic crystal waveguides. And also then, as I'll show you today, we've very recently made superconducting single photon detectors, which are already on the chip and actually can detect single photons with a pretty high 20% efficiency on gallium arsenide. So this is the kind of topics I'm going to try to discuss today. I thought I'd start by saying a couple of things about the different topics in my lab. I don't get time to talk about them all in 45 minutes or so. What we're doing is we're exploring quantum electronic and photonic phenomena. So this is really the two extremes of the types of physics we're studying, as I tried to outline to you. We're growing and making all kinds of tailored materials, quantum dots, nanowires with quantum dots in them, coupled quantum dots, and exploring the fundamental electronic and optical properties of these things. We're, as I'll show you today, some very new results where we've actually been using light to essentially initialize a qubit, also to coherently control a qubit, and also to read out a spin qubit in a single quantum dot. And I'll show you this can be done with very high fidelities, well above 90%, and actually without a magnetic field and over timescales which are of the order of a few picoseconds. On the other side of this arrow, we're doing a lot of work investigating how we can generate photonic crystals, both 2D photonic crystals and 3D photonic crystals, and work I won't talk about today, which is more dealing with metallic photonic nanostructures, that is plasmonics. And as I mentioned, the dream is to put all of this together and make a kind of integrated quantum optics on a semiconductor chip. And this is, as you'll see, far, far away, but certainly the ingredients are there. The challenges start to become putting these things together and actually scaling them. So let me just start by saying a few very general things about the types of nanostructure we're looking at, in particular these self-assembled quantum dots. which we've been probing. Now, I put here semiconductor artificial atoms. These are nanoscale structures. They localize charge carriers, so they have an atomic-like discrete density of states. They have essentially an atomic-like single particle spectrum. However, in many respects, you'll see that they're not like artificial atoms. They couple to the environment, they couple to phonons, and as a result of that, they essentially are like, if you like, atoms which don't move, but the price you pay is that the coherence is not as nice as you would get in the atomic physics communities. This shows a typical example of a simple excitation you can make on such nanostructures. You can excite an electron from the valence to the conduction band. And we're going to talk about this in terms of being an exciton. As you're going to see, this is an exciton which is formed from an electron in the conduction band and a heavy hole in the valence band. And this is pretty important because the confinement in these types of systems, combined with the strain, pushes the light hole band far away, and as a result of that, you can really think about this valence band state as being an orbital state of a discretized heavy hole. These things have a well-defined spin. For the electron, it's an S-like Bloch wave function. It has a spin of plus minus 1/2. And for the heavy hole, it's a heavy hole wave function. It has a spin projection along Z of plus minus 3/2. And this is going to turn out to be very important because it determines the spin selection rules for which polarizations of light couple to which particular spin states of these excitons. Another very important property of these nanostructures is that I've called them non-linear, and they're non-linear at the single particle level. That means that if you change the number of carriers inside the quantum dot, you shift the frequency where it's interacting with light. So for example, if I excite this thing very strongly and create a lot of electrons and holes, I allow these electrons and holes to recombine with each other, typically what will happen is they'll send out a bunch of photons, in this case 4. There's the second one coming out, the third one. There's the so-called biexciton, where there were 2 electrons and holes, and the final photon would give me then a photon at this frequency that I've labeled here 1x. So you see in my cartoon at least, I'll show you some data in a second, they behave a bit like atoms. It's a discrete emission spectrum. And very, very important, they're inherently nonlinear. You saw that the 4 photon, the 3 photon, the 2, and the 1 exciton, they all came at different frequencies. And it's this property, which is coming from Coulomb interactions, which allow us to treat, for example, this single exciton as a 2-level system. 2 levels, the vacuum state, the empty quantum dot, and 1 electron hole pair in the system. And it's this property which actually underpins a lot of the interesting physics you can do with this type of nanostructure, for example, generation of non-classical states of light, and as I'll show you today, accessing and exploiting quantum coherence in this type of system. Now, in order for me to, let's say, justify some of the results I'm going to show you, I'm going to have to spend a couple of minutes talking about the spin structure of this 1 electron, 1 hole excitation, this 1x excitation. Let me do that. This is a diagram which shows typically the excitation energy of one of these excitons. It's in the near-infrared optical region. And if you look at the spin structure of this exciton, it's formed from an electron and a heavy hole, and you can create from this 4 exciton states, 2 of which here I've labeled blue and red. And if you look at them very carefully, you can see that on one of them the electron is basically pointing up, on the hole pointing down, and the other one it's inverted. These excitons both have a total angular momentum projection of 1, meaning you can create them with 1 photon processes. So they're what's called bright excitons in the system. Of course, I can also create exciton states where the electrons and holes point in the same direction, both down or both up, and these states are dark excitons. They don't couple to 1 photon transitions. You can't conserve the angular momentum from the photon to create the exciton. So I'm going to throw these away for the time being and forget about them and deal only with these optically active excitons. And actually the optical selection rules tell you, and this is quite important for what I'm going to show you next, that these 2 exciton states have an optical selection rule such that the blue one you can create with left circularly polarized light, and the red one you can create with right circularly polarized light. Yeah? So you can control the spin of the exciton you create just by controlling the polarization of the photon. I'm going to show you in a short time this is much more general than I'm showing you here. You really can control the orientation of the superposition of the spin wave function, so the point direction of the Bloch sphere this spin points, by controlling the polarization of light. Now, if that was true, everything would be proceeding according to what we know is everything's well and good. It turns out in real quantum dots, they don't have perfect cylindrical symmetry, and there's another interaction which is an anisotropic part of the electron-hole exchange, so the coupling between these two spins, which actually mixes these two eigenstates. And what you create is typically one state which is an antisymmetric combination of the two. It's a horizontally polarized thing, and another state which is a symmetric combination of the two. And these are then linearly polarized. You can excite them with linearly polarized light along certain crystal directions. Turns out it's the 1, 1, 0 and the 1, 1 bar 0 crystal direction.
And you put delta 1 with some uncertainties, but it depends on the crystal structure and is good otherwise.
It depends on the crystal structure, and you see this in reality. So depending on how you control the confinement energy or how you control the quantum dot composition and things, you can vary this fine structure splitting. Yeah?
But I should think of it as fixed otherwise for a given dot.
That's right. Yeah. And what I'm going to show you today is actually, we're going to live with these eigenstates, and it's going to be perfectly okay in terms of controlling the spin. You don't need to get rid of this fine structure splitting to control the spin wave function. Now, if you do want to get rid of it, you can apply a large magnetic field. There's an example of a recent work which shows these two polarized transitions, horizontally and vertically polarized, separated by something like 8 or 9 gigahertz in this example. If you apply large magnetic fields, what happens is at some point the Zeeman energy becomes much larger than this fine structure splitting, and at that point you get an evolution to these pure spin eigenstates again, which can be addressed. These eigenstates then right and left circularly polarized, and can be addressed with right and left circularly polarized light. Okay. I will promise that until now I've shown you no data. Let me show you one piece of data, and then I'll show you some, what I think is very interesting, very recent data regarding the spin control in these systems. This is very, very old data from more than 10 years ago now. It's luminescence from a single quantum dot. And what you see is it has a discrete emission structure, just like I promised you with my PowerPoint cartoon. It arises at very low pump powers. If you pump very weakly, you create single electron hole pairs. They get trapped into the quantum dot and generate a photon, which is the single exciton. That's this transition you see right here. And as soon as you start to pump a little harder, statistically, you populate the quantum dot with a fluctuating number of electrons and holes, and you see what I could call an exciton soup. A very messy emission reflecting the fluctuating occupation of the quantum dot. If I look here really very, very closely at this exciton, here is a measurement at 6 Tesla. You really see very nicely the Zeeman splitting, where you can see these two spin eigenstates I've been talking about, which you could in this experiment excite just by tuning your laser here or tuning your laser here, or alternatively you can control the polarization of your light field and address these spin states in that way selectively. So to summarize very quickly the fundamental properties of these things, they have very strong interband transitions, very large dipole moments. You can control the polarization of the exciton by controlling the polarization of these photons you use to create it. They have this very nice property that they have essentially single particle nonlinearities. Changing the number of particles shifts the transition frequencies apart. And to give you some numbers, line widths are about essentially 1 microelectron volt, and the typical separation here is of the order of 1,000 times larger. So they're very well separated. The excitons and the spin has very nice coherence. I'm going to show you today some measurements on exciton spin coherence. And for later on in my talk, you can embed these things in devices. You can use the Stark effect to control their properties. You can use optical pulses to do the ultra-fast state manipulation on the Bloch sphere. And I won't have time to talk about it today, but you can also stack these things on top of each other and realize coupled quantum systems. So this is the end of my advertisement for quantum dots. I think many of you don't need them selling to you. But what I'm going to show you next is you can actually see quantum coherence, exploit it and use it in this type of nanostructure. So I'm going to move to the first of the scientific topics I wanted to talk about today, which is zero magnetic field. It's all optical, ultra-fast coherent spin control in a single quantum dot. And I want to basically acknowledge it's the PhD work of one of my students, Kai Müller, together with two master students in my group. Now, we've already talked about optically addressing spin. I don't have to this audience, tell you how we do that. We do it essentially via the polarization of the light. And everybody here knows that light comes in different polarizations, different flavors. There's an example, of course, of linearly polarized light, where the X and Y components of the electric field are in phase, they have the same amplitude. I have a polarization vector which occupies a plane. We can think of this, of course, as being a superposition of these two polarization states, horizontal and vertical, and this would be an anti-diagonal linear polarization. Of course, we can create circularly polarized light by introducing a phase shift between the two components. This is another superposition of horizontal and vertically polarized light. And of course, the generic case would be some elliptical polarization described by some arbitrary superposition of these two basis vectors. So, by controlling the phase, we can of course generate very easily, using cheap optics, these different types of polarization states. Now we represent this, of course, either by a polarization ellipses, where we have an ellipticity angle, which is key, and also psi, which is the orientation of this polarization ellipse. And a much nicer way to represent it for my talk today is going to be by using the Poincaré sphere. And that basically is a sphere where you have, for example, along different axes, here you have a right circularly polarized state, a left circularly polarized state, and in the equatorial plane here, the linearly polarized state, horizontal, vertical, diagonal, and anti-diagonal. Now the correlation between the polarization and the spin is quite clear to see. We talked earlier on about the optical selection rules. So you'd imagine if I excite with left circularly polarized light, I've now rotated my Poincaré sphere through 90 degrees just to confuse you. There is L, left circularly polarized, that generates this state. Right polarized light generates this state. And of course I can write horizontal and vertical polarizations as different superpositions of the right and left circularly polarized light. The diagonal polarization can also be written as another superposition. So the main point I'd like to make with this slide is, by controlling the polarization of the light that I shine onto my quantum system, I should create an exciton spin state which is in a particular coherent superposition, providing there are no mechanisms which destroy the coherence of the spin wave function. So this is what we're going to be doing. We're going to be mapping between the polarization and the exciton spin and controlling this arbitrarily and using that to control this. And I'm going to show you that we can actually do this with a fidelity and a precision better than 95%.
So when we describe the polarization of light, we can put it onto a Poincaré sphere, even though it's got spin 1 because it's transverse.
Yes.
And we map it over to the exciton spin, which also has spin 1, but doesn't have that extra restriction, yet it maps onto a sphere. So what are we missing? Because normally we wouldn't expect to be able to map spin 1 onto a sphere.
That's right. I think the thing that we're missing here is typically I'm going to be defining a Bloch sphere for a 2-level system is also something which is a little weird. For a 3-level system is something a bit weird. What I'm doing here is I'm going to be exciting with a pulse which is sufficiently short that its bandwidth is larger than this type of fine structure splitting. So I'm always going to be exciting a coherent superposition of these two levels.
Sure.
Yeah. So that's essentially what I'm going to be doing. So your problem is...
Well, my problem is it's spin 1, so there's more degrees of freedom than can be represented on the sphere. So what degree of freedom, or how should I think of what degree of freedom is not available so that I can map it onto a sphere?
Well, I don't think it is a problem, because essentially what I'm doing is I'm mapping the polarization onto the spin of the exciton. Yeah. And I can write any of these polarization vectors in terms of linear superpositions of these exciton eigenstates. So without the fine structure splitting, these are eigenstates of the exciton, and with the fine structure splitting, these are eigenstates of the exciton.
Okay, so
maybe that's the reason why
Well, yeah, I guess looking at it, the thing that's missing from a spin 1 system is anything that has both spins up or both spins down. So I guess maybe that's the...
That's because what I did is I threw away those dark excitons because they're not optically active. They're also spectrally detuned by quite a large energy.
So it's the restriction to bright excitons that's the...
It's the restriction to bright excitons, and this is a good thing to be able to do. I mean, we've measured things like the relative oscillator strengths, and there's orders of magnitude.
It's a restriction to two states and the neglect of any coupling they might have with anything else.
Exactly.
And otherwise it doesn't matter what they are, it's still like a spin-half system.
That's right, yeah. So it's basically, you could see this as some kind of pseudo-spin half system. Even
Actually, I think it's pseudo-spin.
Yeah. Okay. So let me show you how we do this type of measurement. Well, we're doing ultrafast pump probe spectroscopy. So we're basically exciting the thing with picosecond laser pulses. And we start with ultrafast oscillator, a Thai sapphire, which is delivering 90 femtosecond pulses. It's not this one, but it's one which is much better than this one, delivering 90 femtosecond oscillator pulses. And what we're then doing is we're putting these pulses through a pulse shaper, which is nothing more than a grating to disperse the light into the Fourier plane. And we then take a slit, which is a motorized slit, which can be positioned in front of a mirror, and it picks out of this broadband pulse a picosecond pulse. Yeah? So this is an example. This is the bandwidth of the femtosecond oscillator, and these different transitions, or these different peaks, are what happens when we tune this slit over this mirror, and we pick out picosecond pulses from within this femtosecond envelope. That provides us with one pulse. We can tune over a large bandwidth, much bigger than we need. We then control its polarization. We send it through some optics into a helium can, which has inside our sample on a microscope, and we can focus the light on a single quantum dot and excite it using these pulses. That would be enough, for example, to optically prepare the spin and via the polarization to orientate the spin. We do this again because we want to be able to measure the spin, and we'd like to measure it at some later time. So we have a second one of these which allows us to come with a second laser pulse to measure the spin of the exciton. Again, we can control the polarization, and we have a third one which is going to allow us then to actually control the spin. So it's a 3-pulse experiment: pump, control, and probe. To give you some numbers, we can tune these pulses over a bandwidth of something like 30 milli-electron volts. You probably want to have it in gigahertz, so it's quite a large bandwidth. The pulse widths we can vary from about 0.1 to 0.5 milli-electron volts. This is pulse durations up to about 9 picoseconds down to about 3 picoseconds. And we can excite the system, and these 3 arms are stabilized in phase relative to each other using a HENI to stabilize these. So what do we measure? Well, we excite the system. This is my quantum dot. We have it embedded in a device which has an electric field along the axis. We excite it and create an electron-hole pair, and the spin of this electron-hole pair is defined by the polarization of the pulse we created it with. What we then do is we tune the electric field such that over hundreds of picosecond timescales the carriers tunnel out, and they give us a current which flows in the external circuit. So we excite the system. If we excited it, we should measure a current. And to see how this works, there's an example. There's the energy of my pulse as I tune the frequency of the pulse. You see very nicely at some resonance, I hit this exciton transition and I start to get current. I get current of about 7 picoamperes. And if I tune off resonance again, the current goes to 0. It's a simple linear absorption measurement with a single pulse. Now, a much more interesting measurement is to look what happens when I first pump the system, resonant with this exciton, and then I come later on with a tunable probe, and I'm tuning in the red curve the probe frequency. So the pump was here, and I'm tuning in the red curve the probe frequency, and you'll see now I have a new absorption peak, which appears shifted to the low energy side of the exciton transition. I'm going to be plotting a lot of these pump-probe spectra, and rather than showing you always a blue and a red curve, I'm going to be plotting the difference, let's say red minus blue, which gives me a spectrum which looks something like this. And this is important because what it tells us, if we see a positive going signal here, that's this positive going signal, that's induced absorption. It's new absorption which appeared because I pumped the system. And if I see a negative going signal, that's bleaching. It's an absence of absorption because I pre-pumped the system. And I'm going to show you we can actually directly measure the coherence of the spin by measuring the amplitudes of these currents. Either the induced bi-exciton absorption, 2 electrons and 2 holes, or the bleaching of the exciton absorption. Okay, let me yes, please.
So this is all done on a single quantum dot.
This is all done on a single quantum dot.
And so the currents that are involved are currents that are order of a single electron?
No, these are currents because this is done with an oscillator which is repeating at 80 megahertz or 40 megahertz, depending on what the configuration is. So the typical current amplitudes are 7 picoamperes.
Okay, but each pulse
creates a single
electron. Okay.
And I show you on the next plot, if you just do a single pulse experiment and you measure the amplitude of the current versus the pulse area, you see very, very nice Rabi oscillations. This is basically as I increase the pulse area, I drive the system pi pulse, 2 pi pulse, 3 pi pulse, etc. And you see that for pulse areas up to something like 5 pi, we don't observe any evidence for damping of the Rabi oscillations. So the coherence is very well maintained in the preparation step. From now on, the pump pulse is always going to be a pi pulse. I'm going to be pumping here. I'm going to be pumping it with a pi pulse. And if, for example, I coherently generate with a pi pulse the horizontally polarized eigenstate of this quantum dot, so I'm pumping this on the Bloch sphere, then what I'd expect is I'd expect to see some blocking if I try to then excite the system with a second pulse, which is vertically polarized. This is exactly what we've done, what we've observed. For example, if I apply a pump pulse tuned to this exciton transition, which is horizontally polarized, and then I come with a probe pulse, which is tuned, which is vertically polarized to this other transition, then all I see in my pump probe spectrum is a single dip, and it's a single dip, the bleaching of the exciton. Yeah? If I change the polarization of the probe from vertical to horizontal, what I now see is 2 things. I see now my bi-exciton with HH, because I can pump the system here, and then with the second pulse I can pump it here. And I also see, if you look at the exciton, the dip is twice as deep. And the reason is, if I pump the exciton and I probe it at the same frequency with a second pi pulse, I destroy the population. I drive it back down to 0, the total pulse area would then be 2 pi. So either from the amplitude of this signal, or from the, if you like, the stimulated emission of this signal, I can get information about where the spin vector was, where the Bloch vector was on the Bloch sphere. Now, so far I've not shown you coherence, yeah? There's nothing, I've just shown you maybe populations, measurements of populations in the quantum. Let me just summarize. The pump coherently initializes an exciton spin eigenstate. You see nice Rabi oscillations. The probe measures the exciton spin state. I've not proven that to you yet. I've shown you can measure projections, but I've not shown you can measure amplitude and phase. But you can do it either here via the bi-exciton, or you can do it here via the exciton.
I'm a little confused. Why doesn't the Rabi flopping have implicit coherence involved in the creation of force?
This is. Of course it is.
You
It
just
is.
said that you haven't shown any coherence.
What I haven't shown you so far is that we can measure, if you like, the projection, not just the projection of the spin of the Bloch vector onto one axis, but we can actually measure phi and theta. We can measure essentially where we are on the Bloch sphere. I haven't shown you that yet. Now, if you look at the time dynamics and you look for the bi-exciton, what you see is that at short times, if you pump horizontal, you see this amplitude. If you pump horizontal vertical, you never see it because it's blocked. If I look at the exciton, you see the same. I either see stimulated emission if I go horizontal with a certain decay, and if I go horizontal vertical, I see that the dip is not as deep because I don't have stimulated emission. And what you see from this dynamics is essentially the tunneling time of the carriers. We can change that by changing the electric field we apply to the quantum dot. So what I'd want you to have in your mind is that we can do resonant and non-resonant spin readouts. They exhibit identical dynamics. You can see from these curves, you can maybe believe me that they're identical. It's due to tunneling. And the question is, do we measure spin projection or do we also measure amplitude and phase? Now it's easy to check And the way to check is simply by exciting a superposition of non-degenerate eigenstates. So what we do now, these are the eigenstates of the quantum dot, and we excite this with a right circularly polarized pulse. And what you'd expect to see now is that if you excite purely on resonance, you create a superposition of these two eigenstates, and as a result of that, you prepare the system in the right direction, and it will evolve with a frequency which is given by the energetic difference between these two eigenstates, which is typically 20 or so microelectron volts. That's about 150 picoseconds of periodic precession time. If we do the experiment, now we're exciting right, we're preparing our spin in this direction, we're probing right, probing it in this direction, we see very nicely the stimulated emission. If we probe right and left, we don't see the stimulated emission here, but we now see the biexciton. And if we now look at the amplitude of the biexciton, say, versus time, we see very, very nicely anti-correlated oscillations, which correspond to the oscillation, the precession of this Bloch vector due to the energy difference of these two eigenstates. We can do the same, just to give you the numbers. It's about 150 picoseconds. This corresponds to 27 micro eV. It's very close to what we measure using high-resolution spectroscopy on the same quantum dot. You can also see, if I measure the 1 exciton, the same type of oscillations. This is again due to this precession. So essentially what I'm doing here is I'm preparing the spin in the equatorial plane. It's precessing, and I'm always trying to measure it along the right direction. And as a result of that, whenever it comes back and projection is along the right, I measure an increase in the current. And you can do this either non-resonantly by probing via the biexciton, or you can do it all completely resonantly just by looking at the stimulated emission signal from the exciton. Now, the question now is, can I make an arbitrary readout? Yeah, can I first prepare the spin in an arbitrary way, and can I read it out arbitrarily? So in this experiment here, what I'm doing is I'm always preparing the spin orientated along the right direction, so along here. It's precessing, and I'm reading it out either along the right direction, along the diagonal, the left, or the anti-diagonal. And you see very nicely that there's always a quarter period phase shift between these different curves, which just tells you that the Bloch vector is precessing along this equatorial plane, and you can measure this phase shift. This is done non-resonantly via the biexciton. There is the same data now measured resonantly via the exciton, and I hope you can see there very nicely always a quarter period phase shift when we measure in these different directions. So we really can measure the projection of the spin at a particular point in time.
There's less noise on the right. Is that just due to the scales?
This is because this was the first measurement the student did, and then he went back to the lab and made everything better, and then it came out looking like that. So to give you an idea, if you tell the student this is a bit noisy, here the noise is about 150 femtoamperes, and here it's about 40 femtoamperes. Yeah, he just improved the electronics. Okay, so I want to show you now that we can arbitrarily prepare the spin, and we can arbitrarily read it out. We can prepare it in any direction on the Bloch sphere, and we can read the projection on any other direction on the Bloch sphere. I should get a move on a little bit. There's an example where we're preparing a spin, and we're always preparing at some point in the equatorial plane, and we're varying the angle at which we prepare it. So we're varying the direction phi with which we prepare it. What we then do is exactly at a quarter of a precession period, we measure the projection along the horizontal polarized direction, so the projection along this direction, and we measure the projection along the right polarized direction. And what you see very nicely is first the horizontal polarized direction. There's almost no signal. This tells you that the spin really is precessing in the equatorial plane. There's no, essentially, error. There's a very weak gate error out of the plane. And if I measure along the r direction, you see this very nice cosinusoidal oscillation corresponding to this pre-precession of the spin. We can do the same experiment now, preparing the spin at different directions along this vertical cut through the Bloch sphere. Again measured in the right direction, the red curve, or measured along the horizontal polarization direction, the north pole if you like. And you again see almost no signal when we're measuring in this basis, but measuring in the other basis we see very nice signal. So we really see in this example that you can really measure, you can prepare a spin in an arbitrary direction on the Bloch sphere. Maybe just to give you a number, because I was very impressed, we actually, from the oscillation contrast versus time, we could actually estimate that the spin preparation and readout fidelity is better than 95%. This is just given by the noise, which is on our measurement of the current. We have still 50 femtoamperes of noise, but within that, and we have polarization errors caused by the optics, but without very much, let's say, complicated experiments, we could actually get the fidelity of the preparation and readout to be very, very high.
But on that last one,
Yeah.
it looked like you still had a small wobble in the...
That's right. There is a small wobble, and all I can do is promise you that there is other data more recently where the wobble is completely gone. So there are here some gating errors, probably induced by birefringence in the fibers. You know, we have polarization states which are prepared, and all of these polarized pulses are sent over fibers to the experiment. Yeah. Okay. So we can prepare a spin, we can prepare arbitrary spin states, we can measure with amplitude and phase sensitivity the projection of this spin, and of course the next thing you need to do is to control the spin after you've prepared it on the Bloch sphere. We've done this experiment very recently, in fact a few weeks ago, where we've actually used what is known as the geometric phase approach to control the spin wave function. And in a very, very simple picture, I'm showing you here the crystal ground state, the exciton, and the biexciton. We prepare the spin using a polarized pi pulse. What we then do is we make spin control by coming with a polarized 2 pi pulse, which can either be resonant with the exciton, it drives the system essentially via these levels, or we can also control the system via another transition, say the exciton to biexciton transition. And the polarization direction of this 2 pi pulse is what controls essentially where I move the Bloch vector on the Bloch sphere. I then make the measurement with a second pi pulse, essentially to this and this I've just shown you. This is something which I'm just about to show you. Now, this theory of this geometrical phase approach, essentially the way to think about this is the pulse acts for a certain time, and during the time the pulse acts, one of the 2 polarization components of the exciton is essentially varied. Yeah? The other one is kept constant. It turns out when you do the math, if this is the direction of the control pulse, that's the polarization direction, what you do is you essentially rotate the Bloch vector around this blue direction. And of course, the blue direction I can choose arbitrarily by controlling the polarization of the 2 pi control pulse that I apply to the system. Let me show you our first experiments. This is very new data, so you're also seeing it for the first time today, like me. This is an example of the pulse is applied at 50 picoseconds time delay. You saw that it was excited along the diagonal direction. We manipulated at 50 picoseconds time delay and measured along diagonal. This is this oscillation due to the precession of the fine structure splitting. And at this point here, we varied the orientation of the control pulse. And what you can see, which is very nice, is as I vary the pulse from the angle of the control pulse along the theta direction, from 0 to pi, I get a very, very nice 2 pi shift of the phase of the wave function. What you can also see is the amplitude of these oscillations doesn't depend on the angle through which I rotate the thing. We really have, along the phi direction, very good coherent control. If you look now, making theta control, so controlling this angle along the Bloch sphere, again the pulse is applied at 50 picoseconds. What we've then done is we've made measurements up to pi over 4 angles, and if you change the polarization of the control pulse to pi over 4, you should rotate the Bloch vector to the north pole, essentially this H polarization state. You see at that point the oscillations stop, because you're now in an eigenstate of the system. And if you keep rotating beyond the north pole, the oscillations come back, but they have the opposite phase. So I've shown you that we can control the spin of the wave function both in theta and also in phi. And we can do this again, if we analyze the numbers, we again have our estimation of the fidelity. These are not clean numbers, they're numbers we calculate, or me on the plane. It's given by the noise, it's about above 90%. I've called it 95%, so we're kind of all friends here, so let's call it 95%. Okay. How am I doing for time, Glenn?
Oh, yeah. 10, 15 minutes.
Oh, great. Okay. So, what I've just shown you is actually very new data we've just measured in the last month or two, where we've shown at zero magnetic field we can map the polarization state of light faithfully to the spin of the exciton over 3 picosecond timescales. I've shown you that we can get very, very high fidelity spin initialization, we can do arbitrary rotations on the Bloch sphere, and we can do readout, and I also shown you that you can do all of this with one frequency, pumping the exciton, controlling the exciton, and measuring the exciton. So you don't need to use different color pulses, you can do all of this with 3 pulses tuned to the same frequency. Okay. Seems I have 15 minutes. I want to also talk a little bit about other topics which are being studied in my group. We've also been working on cavity quantum electrodynamics using quantum dots embedded in photonic crystal resonators. And we've been trying to do this age-old problem of getting light out of silicon using cavity QED phenomena. And in this case, we've been collaborating with the group of Yasuhiko Arakawa in Tokyo to make silicon-based 3D photonic crystal resonators. I always remember when I first went to Munich as a postdoc back in the late 1990s, a very established professor, Fred Koch, who was working a lot with silicon, told me the only way to get light out of it is to drill a hole and put a bulb behind. Yeah? It turns out, if you try to use cavity QED effects, you can improve things. It's still not a great emitter. Yeah? So I'm telling you that in advance. Let me say a few words about the different experiments we've been doing here. Let me say one experiment which has been done by Arne Laucht in my group. Okay, I'm not going to talk about this because of the interest of time. Everybody here, I guess, knows that if you put an emitter in a cavity, you modify the mode density. If you modify the mode density, you can control the spontaneous emission. Yeah, it's what's known as the Purcell effect. And essentially, you can use these cavities to either enhance or to suppress spontaneous emission. And the most important thing is that you need cavities which are very small, because the amplitude of the vacuum field fluctuations are inversely proportional to the volume. Yeah? So the smaller the cavity is, the larger the amplitude of the vacuum field fluctuations, and the more control you have over the spontaneous emission lifetime. At the same time, if you make single mode cavities, you can control the photon density of modes, and by doing this, you can switch on and off spontaneous emission in a solid state system. Let me give you a couple of experiments we did over the last few years. This is an example in the weak coupling regime of cavity QED. It's a photonic crystal L3 cavity like this with a quantum dot inside. This is the quantum dot we're going to be looking at, this blue transition. And this red line shape here is the cavity mode, which we can tune in and out of resonance with this exciton transition. And we can measure the lifetime, the spontaneous emission lifetime, as we shift this in and out of resonance with the exciton transition. The data is shown over here on the right-hand side. Let me walk you through this. That's the emission lifetime in nanoseconds, 1 to 5 nanoseconds. That is the detuning between the quantum dot and the cavity. And what you see very nicely is, as you have it on resonance, the lifetime of the quantum dot is very, very short. If you start to move the cavity away, here it's moved to 4 milli-electron volts detuning. That's about 15 line widths. The lifetime gets a bit slower. If you move it further away, the same quantum dot emits much more slower. And if you move it very far away, the lifetime becomes something like 12 nanoseconds, extremely long. And this is the same emitter, and actually it shows you that you can use this to control spontaneous emission. There's actually a lot of interesting physics which goes on here regarding the range over which you can have a Purcell effect. If you look at that, I see Purcell effect in this experiment for detunings more than 40 line widths of the cavity mode. And in atomic cavity QED, basically as soon as you detune by a few line widths, there's nothing else happening. The physics here was finally resolved a few years ago. We published a couple of papers where we showed that phonons play an important role in this extra bandwidth where the Purcell effect is active, and also the fact that this is not really a two-level emitter, it's a multi-level emitter, and they all can couple to the cavity.
Can you say a word about the picture at the top left, exactly what we're supposed to interpret that as?
This one here?
No, the graph there.
That is the cavity. So we have basically it's a membrane of semiconductor which you drill holes in to make a photonic band gap. And this region here confines a single cavity mode because of the distributed Bragg refractor in all directions. So it's a very small cavity. To give you a length scale, that is of the order of 500 or 600 nanometers. Very small.
So does the temperature, because the number of phonon modes occupied, affect the phonon?
It does indeed. It does indeed. You really see, for example, at low temperature, there's a strong asymmetry between red and blue detuning because you can only have phonon emission. You don't occupy the phonon states. And if you raise the temperature, it becomes symmetric. And the kind of message is, for these types of quantum dots, the strongest coupling to phonons happens for energies of 2 or 3 milli-electron volts. And this is such a low energy that even at 10 Kelvin, 15 Kelvin, you excite these phonons anyway. Yeah? So the bandwidth is much larger than in
But this is done at constant temperature, or this is done by tuning?
This is done at constant temperature by tuning with gas deposition. What we do is we basically freeze nitrogen inside this thing and can tune.
And it's 4 to 10 Kelvin.
The temperature here is fixed. It's actually about 10 Kelvin in this experiment. Now, you all know, I don't have to tell this audience, that when you have a situation where the radiative lifetime into the cavity mode is so very short, and the radiative lifetime into all other modes is very, very long, on resonance, something like in this case, 98% of all the photons are emitted into the cavity mode. And this is something which is well known. There are lots of very nice dreams I share for doing on-chip quantum optics. We've also managed to do this types of experiments not just in the weak coupling regime, but in the strong coupling regime of light matter coupling. This is an example from a paper from a couple of years ago. You all know what should happen if you make the cavity Q larger and larger, higher and higher and higher. At some point you should get vacuum Rabi oscillations between the cavity and the quantum dot emitter. That should result in the formation of polaritons in this system and a splitting of the mode spectrum when the cavity and the quantum dot exciton come on resonance. We like that because it's a kind of entangled state. One word, in this experiment, I'm actually going to show you strong coupling in an electrically switchable system. So by varying the voltage, we can use the Stark effect to tune the exciton in and out of resonance with the cavity mode. And this is something we developed a couple of years ago. There's an example of data. This is actually some of the nicest data we managed to get. There you see an exciton. As you vary the voltage applied to this device, you tune the frequency of the exciton because of the DC Stark effect. And when it comes onto resonance with the cavity mode, you see there's a nice avoided crossing, and that is essentially the point at which you have coherent oscillations between the vacuum field and the exciton in the system. Okay. I think in the interest of politeness, I'm going to just jump ahead a little bit. You had a free lunch, but you have a limited patience, I'm sure. So I'm going to move on and just show you very, very quickly what I think is a nice development. I'm going to move on across all of this. I hate people that do this, but I'm now one of these people. I'm sorry about this. I mean, maybe I say this on the way. I'm doing exactly what I hate, but I'm going to do it anyway. We've also managed to make single photon generation into a waveguide. This is a photonic crystal, a very long waveguide. And we've obtained that 60 times more photons go into the waveguide mode than into other modes. So this is deterministic single photon generation on a chip with photons piped in a certain direction. And what's missing, which is the thing I want to sell to you at the end of my talk, is that we have these quantum dots. These things are very nice. They emit single photon states. They emit entangled photon pairs. This is something many of you will know. It's very, very difficult to get the photons out. And at the same time, these photonic crystal nanomaterials that I didn't really explain or describe provide a lot of opportunities. There's an example of a device we've made where we have a couple of waveguides. There's one waveguide, there is another, and there's a cavity which is evanescently coupled to these waveguides. You can also make beam splitters using these photonic crystal structures. And in principle, if you had a detector on the chip, you could put all of these together and start to do optics on a chip. And then you don't tell the funding agency this because you need your lab and you need all your fancy laser systems and things. But a dream would be to generate single photon states, distribute them on a chip, and also measure them on chip. If you want to measure them, you need one of these things. And very recent results, if you could do this, you could do things like this, kind of like quantum interference between two photons on a chip. Very recently, in fact a year ago, we started a project to make these single photon detectors integrate them into waveguides of photonic crystals. And there the challenge is growing superconductors like niobium nitride on gallium arsenide. There's a huge lattice mismatch, about 27% between these two materials. But we managed to obtain very thin 4 nanometer thick films with a TC of 10 Kelvin that is thin enough and sufficient quality to do single photon detection. There's an example of the first device we made in November last year. There's a waveguide. There's the end of the waveguide. If you zoom in here, you can see one of these meandering superconducting nanowires. And we've just finished characterizing this thing, and actually we've managed to obtain that you can get single photon detection on gallium arsenide. Maybe I cut to the chase. The detection efficiency is 21% for this first device we managed to make. So this is detecting photons at 1 micron in the waveguide with a 21% detection efficiency. So I'm very happy about that. I'm going to stop there because you're going to all leave or, be unhappy with me. I was invited here, so I don't want to make myself too unpopular. So let me jump over all of this stuff, and let me just thank the people who really did this work. So the very new results that it looked like I also saw for the first time today, they're about a month old, and they're the results from this guy Kai Müller on the coherent spin control. The results I showed you on photonic crystal nanocavities are from this guy Michael Kaniber. This is the rest of my group. They're all very talented and fantastically nice, wonderful people. Let me thank them, and let me also thank you guys for staying so long and for your attention. Thanks very much.